Good day, sir. My name is Pukwendebe Lucas. In fulfilling the requirements for the midterm homework on EEE 518 digital image processing, I'm going to do exercises on the book Fundamentals of Digital Image Processing, a practical approach with examples in MATLAB. The exercises will cover Chapter 1, Image Representation, Chapter 2, Image Formation, Chapter 3, Image Pixels, and Chapter 4, Image Enhancement. To continue on this presentation, let me quickly go to the exercises in chapter 1. The exercise in chapter 1 is on page 18. I will, I will zoom into this picture, this presentation, so that I will be visible. Exercise 1.1 reads, using the examples presented for displaying an image in MATLAB, together with those for assessing pixel locations, investigate adding and subtracting a scalar value from an individual location, that is, image I, j equals image I, j plus 25, or image I, j equals image I, j minus 25. Start by using the grayscale cell.tif example image and pixel location 100, 20. What is the effect on the grayscale color of adding and subtracting? Expand your technique to the RGB color images by adding and subtracting to all three of the color channels in a stable example image. Also, try just adding to one of the individual color channels while leaving the others unchanged. What is the effect on the pixel color of each of these operations? To provide solutions for exercise 1.1, I'm going to share my MATLAB screen. So this is my MATLAB screen. I'm going to open the folder here, the exercise 1.1 solution is. Adding and subtracting an image grayscale. First of all, we will read in this image using the imRead function. This is our image. And this image is a 159 by 191 unsigned integer 8 image. That means it has representation of the pixel locations between 0 and 255. As you can see. Next, I'm going to add a scalar 25 to the image. By adding a scalar 25 to the image, you can see that there is not much difference between this image and the original image. There's no much difference between this image and the original image. So, to really buttress the point of this exercise, I'm going to increase the scalar to 255. By increasing the scalar to 255, let's look at the example image. Let's look at the result of adding 255 to the image. You can visibly see that there is a white pixel around this location as compared to the original image. where there is nothing like that. Likewise, the pixel, subtracting 255 from the pixel location, you can see a black spot which is pixel location 100,20, which now has a black pixel because we've subtracted a scalar of 255 from it. So adding the scalar to a grayscale image increases the pixel level, and subtracting 255 from the image reduces the pixel level to near zero or near 255 for white and zero for black. Adding and subtracting an image for an RGB image. We're first reading this RGB image using the read function. We're reading the image again. And the image is not show. Yes, this is our image. As you can see, our image is of size 135 by 198 by 3 and is an unsigned integer 8 image. Now let us add a scalar to the image, to all the channels in the image. We are adding the scalar at pixel 120 throughout all the channels from 1 to 3. As you can clearly see, there is a red dot in green pepper showing here. This is a white dot in the green pepper showing that the pixel at this location has been increased from whatever value it is to 255. So subtracting 255 at that same pixel location to, across all the channels, you can see a black spot in the green pepper showing that the pixel at that location has been reduced to almost zero value. Now adding a scalar to only the red channel. Let's investigate the effect of adding the scalar to only the red channel of the image. So when we look at the image, the result of the image, we can see that here the amount of red components of this pixel has increased, and you can see a red dot here showing that the red component of this pixel has increased from whatever it is to nearly 255, which is the highest value for a red pixel. Doing the same for the green channel, you can see a green dot on the green pepper showing that the image pixel level at that location 120 has increased. Then doing the same to the blue channel, you can see almost a very light blue color on the almost white color on the green paper, and that location 120 showing that the pixel value of the blue component has increased. So generally, increasing adding a scalar to a color image either through the channel or through across all the channel or across individual channels increases the pixel level to a very high number, which is 255 for on-site integer 8. So let's investigate subtracting an integer a scalar from the image across the red channel. You can see that there is a light blue or light green color in the image showing that at that particular pixel location, the red component is near 0. Then doing the same for the subtracting the scalar from the green channel of the image, we'll see a blue dot on the green apple showing that the green channel at that pixel location is almost 0. And the pixel in that channel is overshadowed by the blue component of the pixel location at that position. Subtracting the same from the blue channel, you can see a black dot on it showing that the blue component of this pixel is 0. You can as well show this figure instead of running it on the command window by just running the Python running the MATLAB script, and all our images will be displayed on this part of the image on the script window, like editor. So looking at exercise 1.2, sorry, exercise 1.3. Using the grayscale cell.tip example image, investigate using different false color maps to display the image. The MATLAB function color map can take a range of values to specify different false color maps. Example, help, graph 3D, and look under the color maps heading to get a full list. What different aspects and details of the image can be seen using this false colorings in place of the conventional grayscale image? False color maps can also be specified numerically as parameters to the color map command. Enter help color map for further details. To investigate the effect of the color map MATLAB function color map on an image, let's head over to the MATLAB Windows to see how we can do that. So I'm going to clear all variables, clear the screen, close this. Like the example, like the exercise says, we are going to read in the cell.thief image, which has a default color map of gray. So this is the gray component of this image. Let me run this live script so that we can easily see the color map on this other part of the image. So this is our example image as a grayscale using the color map jet. This is what the cell looks like using the color map jet. The same applies to Varuna. We can look at this in a window. We can also investigate HSV. This is how the cell looks using the HSV component of the color map. Using the hot component is what an example image looks like. Using the bone component is what our example image looks like. Using the copper, our example image looks reddish brown. The pink color map, you can see the cell is tending towards the pink color. The white color map gives us a background of white. The flat color map gives us a noisy image which cannot be easily viewed. The lines color map gives us another noisy image which we can now view. The color cube gives us a representation of the color cube, and we can see the segmentation of the cell. And we can also see that the color map function can also take a string which is put in quotes and also take a parameter like this also. This is how the cell looks like using the color map VGA. And we look at the color map of the prism. This is also a noisy image. Look at the color map of autumn. You can see it's almost red. Spring. Spring color map gives us this. The winter gives us an almost blue cell image. The summer gives us an almost green cell image. Then using parameters to index to the color map, 100 gives us the red image. Since the first color channel is 1, is first color channel 1, which is red, and the blue and green channels are 0. The output is a red color mark. We use the 3 RGB colors together, we will get a white color mark. So that is that for exercise 1. We'll now look at exercise 2. The exercises in chapter 2 is in page 46 of the textbook. I'm going to look at exercise 2.2. Exercise 2.2 says, the engineering of image formation poses limits on the spatial resolution of an image through the digitization process. And the limits of spatial resolution, certain image details are lost. Using the MATLAB example image, football.jpng, JPG, and text.png, experiment with the use of IM resize function, both in its simplest form, using a single scale parameter and using a specified image width and height, which is rows and columns. As you reduce image size, at what point do certain image details deteriorate beyond recognition or comprehension within the image? You may also wish to investigate the use of IM resize for enlarging images. Experiment with the effects of enlarging an image using all 3 of the available interpolation functions for the MATLAB IM resize function. What differences do you notice? Also try timing difference resizing interpolation options using the MATLAB TikTok function. So to solve this, we are going to go back to the MATLAB window. Size 2.1. Size 2.2. So we are going to investigate the use of IM resize function. So the first thing we'll do is to read in the example image. And we display 2 example images. So these are football.jpg image. These are text.png image. Text.png image is a binary image, and the football image is a color image. Now, if we want to use resize to reduce the size of this image by a factor of 0.5, and of course, we need to time the operation of this. We can resize both using the resize function. As you can see, the images are smaller than the original image. The original image for text.png is a resized image. Maybe I should make it obvious so that this is the resized image. This is the original image. For the football, this is the resized image, and this is the original image. Now, investigating when the image will no longer be recognized, we use a factor of 0.05 to resize the image. And previously, you can see that it took 0.07 seconds to resize images A and B. So resizing the two images by a factor of 0.05 and showing the images, you can see that the images are not recognizable. They are not recognizable. As you can see, you cannot really distinguish the ball in this image. When downsized by specified width and height, that means you are going to use the number of rows and columns. You also notice that the time it took for this operation is less than the time it took for reducing it to 0.05. You can see that the time it took to downsize from 0.5 to 0.05 is lower. That means as the image size reduces, the amount of time it takes to resize it decreases as well. So resizing this image using specified width and height, and of course timing the image. Image 1 is of width 50 and height 1, while image 2 is of width 50 and size and height 20. You can see also that the images are unrecognizable. If we increase the height and width of the image, we can see also that it took 0.05 seconds, whereas the other one took 0.013 seconds, meaning that resizing from by specifying height and width actually takes longer time than resizing using a factor. And the color image took a longer time to be resized more than the binary image, which is the text.png. So increasing this, you can see that we have resized this image to have the specified length and width, and the same as this, which is different from the original image. Enlarging an image, you can also enlarge an image by specifying a bigger length and width or using a factor. So investigate this. Let's try and resize image A with a height of 100 and a width of 1000. The height of 1000 and a width of 1000. As you can see, it took 0.05 seconds for this image to be resized. Image. Once again, if you need to keep inside. If we show the image, you can see that the image is far bigger than the original image. And if you also enlarge by a factor of 2.5, you also see that it took 0.04 seconds to enlarge that image by a factor of 1000 by 1000, whereas it took 0.05 seconds to enlarge the binary image to the size of 2.5. And when we show the image, you can see that the image is far bigger than the original image. So that is the end of exercise 2. You can visit exercise 3, which is pixels, and the exercise of this chapter is on page 81. Exercise 2.1 says, using the examples presented of arithmetic operations, you can investigate the use of these operators in a variety of ways. First, load the MATLAB example images rise.png and cameraman.tif. Investigate the combined use of the MATLAB im resize and size functions to resize one of the images to be the same size as the other. The MATLAB command whos used in the syntax whos_v will display information about the size and type of a given image or other variable v. Try adding both of these numbers together using the standard MATLAB addition operator and displaying the result. What happens? Now add them together by using the im_add function, but adding a third parameter for the function of int 16 or double with quotes. This forces an output in a 16-bit or floating point double precision data type. You will need to display the output using the image_sc function. How do these two addition operation results differ, and why do they differ? Repeat this exercise using the standard MATLAB subtraction operator and also by using the im_subtract function. To solve exercise 3.1, we'll head over to the MATLAB window. As you can see, first of all, we're reading the cameraman.tif image. We're also reading the rise.png image. Then we'll use whos_a and whos_g to look at the properties of the image. Then we'll use the im resize function to resize the images. We'll add the images together using the normal image operator plus. We'll also add the images together using the im_add operator. We'll do the same for the subtraction, normal subtraction, and also do the same for im_subtract. The two images are this, the cameraman.tif image and the rise.png image. The whose command gives us the size of the cameraman.tif image, which is 256 by 256. It gives us the number of bytes and gives us the class, which is an unsigned integer 8 image. The image, the rise of PNG image is of the same size, 256 by 256, and the same number of bytes, and is also an unsigned integer 8 image. Using the resize function, we can resize those images by giving them a height of width of say 300. So we resize the cameraman image A to a size of 300 by 300, 300 width, 300 height. We resize the rise of PNG image to a size of 300 width, 300 height. Now we can obtain an image W, which is the arithmetic addition of image B, which is obtained from resizing the cameraman.tif image, and image C, which is obtained from resizing the rise.png image. And the result is this image. As you can see, the rise has been added to the cameraman.tif image. And if you inspect the pixel locations, you can see that some of the rise images have a higher pixel than the cloth of the cameraman. Now using add operator and using the double parameter, that is converting the image to a double, you can show that example image. As you can see, the image pixels are more than between 0 and 255. So that means that adding numerically using the addition operator truncates the numbers which are above 255 to be within 0 and 255, while adding with while changing the image to an unsigned integer increases the pixel values to above 255. Using the same addition for unsigned integer 8, we also get the same output. So the user using a double or unsigned integer system gives us the same result when added. Now using the subtract, using the normal subtraction operation, you can see that the lower numbers, which are maybe towards -0, has been computed to be between 0 and 255. You can see the right image and the image is darker. Most of the right on the image are 0 pixel. We have the cameraman image still within the grayscale range of 0 and 255. Using subtract, we can see that Same thing happens. The eyes are within zero range. But the pixels on the cameraman image is higher, the higher pixel than using the normal subtraction of the image. So moving over to the second exercise in chapter 3. Building upon the logical inversion example presented in example 3.6, investigate the application of the IM complement function to different image types and different applications. First, load the example image pepper.png and apply this operator. What effect do you see and to what aspect of traditional photography does the following image coloring relate? Image inversion is also of particular use in medical imaging for highlighting different aspects of a given image. Apply the operator to the example image mir.tif, spine.tif, and cell image 83im409.tif. What resulting effects do you see in the transformed images, which may be beneficial to a human viewer? The solution for exercise 3.1 will be within our MATLAB window. First, let me clear the variables from 3.1 and close 3.1. So in this exercise 3.2, we are investigating the application of the IM complement function. So we can load the PNG image, and we can show it in the image. And we apply the complement to the image. To apply the complement to the image, we can see that the complement is actually the negative of the original image. That means we can get the original image from the negative. And in traditional photography, this is actually what traditional photographers use in converting an image from its negative to the original image. Most of the time, the film in the traditional camera records images in this inverted form, which can be transformed into a color form after going to the nearby film industry to transform the image. So primarily in a photograph, for photographers, images are stored in this inverted form before being processed into a colored image. So we're reading the MRI.tif image. I will show it. Then we'll apply the complement to the image. You can see that the background of the image has changed from black, from the original image to black to white. And changing this from black to white will allow medical practitioners to review more details in the image which are hidden in the black background. Loading the spine.tif image, and we also apply the complement to the image. What we'll see is the same principle. The black background of the image has been transformed into a white background for easy visibility of the structures of the spine, especially for medical imaging systems. We read in the cell.tif, the cell image, 83IN409.tif, and it will apply the complement to this image. The result is a brighter image which allows zoom operation to see much more details in the image than what you have on a darker background, which is what the original image is. So the complement lightens up the image so that more details about the cell can be seen. So this is the end of exercise for chapter 3. Next is chapter 4. The exercises in chapter 4 is on page 109 of the textbook. Page 109. Image enhancement. Exercise 4.1 says, based on example 4.3, experiment with the MATLAB iron noise function for adding different levels of salt and pepper and Gaussian noise to images. Use the pepper's PNG and 8.3 example images as both a color and grayscale example to construct a series of image variables in MATLAB with varying levels and types of noise. You may wish to also investigate the other noise types available from this function. Type doc and noise at the MATLAB prompt. Based on the filtering topics presented in section 4.4, investigate the usefulness of each of the mean, median, and Gaussian filtering for removing different types and levels of image noise. To answer exercise 4.1, let's head over to the MATLAB window. So exercise 4.1 deals with creating a noise to a grayscale image and a color image, and also trying to apply the mean, median, and Gaussian filters to the image. So first of all, we read in our image, which is still.tif, and show the image. Then we apply this salt and pepper noise to the image with a variance of 0.05, and we show the salt and pepper image. We also apply the Gaussian noise to the image with a mean of 0.05 and a variance of 0.02. We also show the Gaussian image, the image with the Gaussian noise. We also put another type of noise, which is the Poisson noise, to the image, and we'll show the image. We also put a speckle noise with a variance of 0.02, and we'll show the image. So let us execute this. I can execute both on the command prompt or by running the MATLAB script. As you can see, this is the original image. This is the original image. This is the salt and pepper image noise in the image. This is the Gaussian noise in the image. This is the Poisson noise in the image. And this is the speckle noise in the image. We also read in the color image and add these noises to the image. So we read the purpose of PNG image, apply the salt and pepper noise to the image, apply the Gaussian noise to the image, also with the same variance and mean, apply the same noise to the Poisson, apply Poisson noise to the image, also apply the speckle noise to the image. We will also display the image. So we can see the salt and pepper noise, the Gaussian noise, the Poisson noise, and the speckle noise in the image. Now it's time for image filtering. So let's first use the mean filter to try and filter the noise in the image. First of all, we define the mean filter, which has a once, this is once of a 3x3 window. I'll take the mean divided by 9. Then we apply the filter to the original image. We apply the same filter to the salt and pepper image. We apply the same filter to the Gaussian image, the same filter to the Poisson image, and the same filter to the speckle image. We plot the output. On doing so, our image will look like this. And as you can see, the grayscale image, the noise in the grayscale image has been smoothened out. When we apply the same mean filtering to the color image by defining the mean filter, applying the mean filter to the original image, apply the same mean filter to the salt and pepper image, apply the same filter to the Gaussian noise image, apply the same filter to the Poisson image, and apply the same filter to the speckle image, and show all the outputs. You can see also that the noise has been smoothened out in the images. So in conclusion, the mean filtering smoothens out noise in the image, but does not remove the noise. It smoothens the noise in the image for easy visibility. Median filtering. We define the median filter using the MFIT2 function, and also define the window size, which is a 3x3 window. We apply the filter to the original, to the salt and pepper noise image. We first apply it to the original image, we apply to the salt and pepper image, apply to the Gaussian noise image, we apply to the Poisson noise image, we apply to the speckle noise image. After applying these filters, the output looks like this. This is the original image, this is the salt and pepper noise image, and as you can see, the median filter has removed the salt and pepper noise in the image, but the median filter could not remove the Gaussian noise in the image. We remove the Poisson noise in the image, and we remove the speckle noise in the image. Applying median filtering for color images. Median filters are applied to color images in a different way. First of all, we have to extract the channels of the image we want to filter. We extract the red channel. We extract the green channel, sorry, green. We'll start the green channel and we'll extract the blue channel. Blue channel. Then we'll now apply the filters along the channels of the image. Applying these filters to the image, you can compare the original image with the filtered image. And as you can see, for the salt and pepper noise, the media filter has been completely removed the salt and pepper noise in the salt and pepper image. Applying the same to the poison noise image. And plotting it, you can see that the noise in the image have not been removed. Extracting the channels, the red, green, and blue channels, and applying the filters to the speckle noise in the image with the speckle noise. We can actually also look at the figure, and we can see that the noise is still in the image. The media filter did not remove the noise in the image. So in general, the media filter removes salt and pepper noise in an image for both the grayscale and colored images. The Gaussian filter. The Gaussian filter is defined by using the X special function, specifying the Gaussian, specifying the window size, and specifying the real width. The Gaussian window. We also apply the filter to the original image, apply the filter to the salt and pepper image, we apply the filter to the poison noise image, apply the filter to the speckle noise image, and if we plot the output, you can see that this is the original image, this is the salt and pepper noise image, this is the Gaussian noise image, this is the poison noise image, and this is the speckle noise image. And as you can see that the Gaussian filter did not remove any of the noises, instead it's smoothing the noises in the image. Applying the Gaussian image filtering to colored image, we also define the filter as before, apply it to the original image, apply filter to the salt and pepper image, apply filter to the Gaussian image, apply it to the poison noise image, and apply it to the speckle noise image. Lastly, we can look at the image output, and we can see that the Gaussian filter did not remove any noise in the image, rather it's smoothing out the noise in the image. In conclusion, the mean and Gaussian filter smoothing noise in the image, whereas the median filter actually removes noise and salt and pepper noise in an image. The last result of this is exercise 4.2. Implement variables. So let's talk about exercise 4.2. Exercise 4.2 says building an example 4.2. Experiment with the use of the different neighborhood dimensions and effect on the resulting image output using the plotting functions of MATLAB. Function plot. and the MATLAB timing function, TikTok. Create a plot of the neighborhood dimension n against operation runtime for applying the min, max, and min functions over an example image. Does the timing increase linearly or not? Why is this? To answer this transfer point, let's head over to the MATLAB window. So as before, we are going to do the cameraman image. We are going to apply the neighborhood, the maximum function. We define the neighborhood and apply the maximum, the mean, and the mean function to the image. So I'm going to run this live script so that you can be able to generate our images for us. As you can see, we defined the neighborhood function, the neighborhood, which is a 3 by 3 neighborhood. Then we'll set the filter, the function filter, which takes the maximum, which uses the maximum function to implement the filter. That means it takes the maximum values within a 3 by 3 window and applies it throughout the image. So loading this image and loading the result of the output for a 3 by 3 neighborhood, you can see that the image, the pixel values of the image have increased. The image is sound brighter than the original image and is blurred. Likewise, applying, and the time it took was 12 seconds to apply. Applying the mean function to the image, we read in the cameraman image, define the filter to the use, which is the minimum function, and we apply it, the neighborhood filter, over the image, which has been read to the cameraman.tip image. We use the TikTok function to time the image, and we will plot it. You can see that using the minimum reduces the pixel level in the image, and the image gets darker than before because we are using the minimum of the pixels within the window. Using the mode of 3 by 3 and applying the mean of the pixel, that is the average value of the pixels over that 3 by 3 window for each pixel in the image. We are plotting the output. You can see that applying the mean filter blurs the image and actually increases the brightness a little bit, as you can see. Is the image, when you expect the pixels here, you can see that pixel here is 230, 167, the pixel here 186, which shows that the pixel value increased while adding the mean, while using the mean filtering to go through the image. Define another neighborhood cell of a 7 by 7 data. I'm applying the max function. You can also see that applying the max function should increases the amount of pixels in the image, but the image is blurred as compared to the original. That means that the number of neighborhood sizes increases, the blur level of the image increases using the max function. If we read in another command image with a neighborhood size of 7 by 7, using the minimal function, you can see that the pixels are darker than the original pixels, which follows from a neighborhood size of 3 by 3. You can see that the neighborhood size of 7 by 7, the pixels are darker than for a neighborhood size of 3 by 3. Applying the mean, you can see that increasing the neighborhood of the mean totally blurs the image, has a blurring effect to the image. Now let's plot time against the number of neighborhoods. For the maximum function, you can see the line plots of neighborhood against time. So for pixel level, for a neighborhood function of 3 by 3, the time it took was 12.32 seconds. Whereas for a neighborhood time of 7, it took 2.67 seconds, which means that as the number of neighborhoods increases, the time it takes decreases. To apply the maximum function decreases. Plotting the mean function against the number of neighborhoods, you can also see that the same principle applies. It took 3.37 seconds to apply the 3 by 3 neighborhood and almost 2.5 seconds to apply the 7 by 7 neighborhood. We also plot the mean function, as the average function against time. The same principle applies. For a neighborhood side of 3 by 3, the time it took is 5.5 seconds. And for a neighborhood size of 7 by 7, the time it took is 4.354 seconds. So generally, as the number of neighborhoods increases, the time decreases, and the mean, max, and average data applied to the neighborhood causes it to increase in brightness, reduce in brightness, or become blurred. This ends the review of the exercises for chapters 1, 2, and 3. Thank you very much, sir.